All right, in this video, we're going to take a look at some areas of some known cross sections. And we've got some nice graphics, compliments of mapdemos.org. And here we have a three-dimensional solid that's being made. It's being made by stacking squares on top of this triangle made by two lines, okay? So we need to find the area of this, all right? I'm sorry, the volume of all this, all right? So that's, we know the cross sections are squares. So we got this shape right here, and we're going to stack some squares on this, okay? So what we do to do this is we're going to imagine one line segment, so one little piece, okay, or a rectangle actually. Okay, so imagine that that's a little rectangle, and we're going to stack a square on top of that. Okay, so to find the area of the square, all that we really need to know is we need to know the length of that side. So we got to find the length of that side, and so we can do that, no problem. Let's try that. Let's call that S. And so this right here, by the way, this would be given in the problem is y equals 1/2 x, and this is the graph, y equals negative 1/2 x. And we're going to do this up to 5. So we're going to consider the graph from 0 to 5. Well, how long is S? That's not terribly tough. The length S there is going to be the top line, 1/2 x minus negative 1/2 x. Now, we're finding the length in terms of x because this length will change. See, the side of each of these squares is always different. So it depends on where on the x-axis you're going to choose this, all right? And so we have S is just, well, this is just going to be 1x. Well, that's handy. That's a pretty simple one. This is about as simple as it gets. And so that's the side. S is equal to whatever x is. So the area of one of these squares, again, if we imagine this square that's going to stack on top of that, the area of one of those is going to be x squared. It's s squared. Let me write it this way. S squared. And that's, since s is the same as x, that's x squared. Well, we're just going to add the area of all of these up. Okay? So the area of all of these, when we add up values, we're talking integral. So the volume is just the integral from 0 to 5, because that's our bounds, of x squared. We're going to add up all of these areas, because when you add up all the areas, you get volume. All right, so that is using the fundamental theorem of calculus. That is 1/3 x cubed, and that is from 5 to 0. And so this is going to be equal to 125, that's 5 cubed, over 3, minus 0 over 3, but 0 over 3 doesn't matter. So there is our volume. Okay, that's how you do it. So now let's find the volume of another cross section with another nice graphic from that mathDemos.org. Okay, give them credit there. So here we're going to stack semicircles, half circles on top of this graph. All right, so we get this kind of, I don't know what that is, kind of a cornucopia looking thing there. All right, this arch looking thing. So we're stacking circles on top of this, or semicircles actually on top of this. Okay, so what we got to do is we got to figure out what the radius of the circle is. So we're going to figure out two things. We're going to first find out what, let's call this S. We'll use the same letter. But then we need to cut that in half, because we need to figure out what R is. This little distance right here, the radius of that semicircle that we're going to stack on top. Well, in this case, this is the graph y equals the square root of x. And so the length S is just the height of the curve. All right? So we're going to go S is just the square root of x. So we're writing this in terms of x. Well, the radius is half that length. So the radius is 1/2 times the square root of x. And there you go. And so now we can find the area of that semicircle. So find the area of one circle, one semicircle that is, and it's going to be, area of a circle is pi r squared. This is 1/2 pi r squared. This is for a semicircle. All right. And now, so well, what is the radius? Here's the radius down here. It's 1/2 square root of x. So we're going to substitute. So the area of one slice, one cross section, is pi times 1/2 square root of x. That's the radius squared. So in place of the radius, we put 1/2 square root of x. Now let's clean that up. 1/2 squared is 1/4. So we got 1/2 pi times 1/4. And the square root of x squared is x. So this is just going to be 1/8 pi x. Well, that's one slice. We want all of these slices, but because this is in terms of x, we can add all these up. You can use our integration. We're just going to integrate from 0 to 5, because we're going to go to 5 here. Chose 5. I don't know where this is. There's no marks on the graphic, but let's go to 5. From 0 to 5 of, let's see, 1/8 pi x dx. All right. So that's going to be 1/8, and we're going to have pi times 1/2. So 1/2 times x squared. And we're going to do that from 0 to 5. Okay, using FTC1, that's going to be 1/16 times 25 pi. And minus, we've got to substitute 0 in here. When you put 0 in for all this, you get 0. So we're really subtracting 0 from that, but that doesn't change anything. So there we have it. Okay. So that is a semicircle. The key with the semicircle is you got to find that length S and cut it in half to get the radius. Don't forget to cut it in half. And don't forget your area is not pi r squared, it's 1/2 pi r squared. Now for the most challenging one. We're going to stack some equilateral triangles on this shape. And we're going to get a funny looking wedge like this. So we're going to build this three-dimensional shape by stacking equilateral triangles on top of the graph y equals the sine of x. Now, we would like to know S. Well, in this case, S is pretty straightforward. It's just the sine of x. All right, nothing fancy. We're not subtracting two graphs here. Pretty straightforward, okay? If we had two graphs like we did in the first one, we'd have to subtract them. All right, so now the challenging part here is to talk about the area of a triangle. So how do you find the area of a triangle if you know its side? All right, well, an equilateral triangle, if we have side S, okay, so if that's S, then this is S over 2. We've got a 30, 60, 90 triangle here. So this guy right here, this altitude is going to be half of the base times the square root of 3. Remember that from, probably Algebra 2 and square 3s over 2. Okay, so that's the height. Okay, from geometry or Algebra 2 or even pre-calculus, you use that square root of 3 over 2. So the area is half the base. Area of a triangle is half the base times the height. And so the area of an equilateral triangle here is S over 2, that's half the base, times the height, which is the square root of 3 over 2 times S. So the area of an equilateral triangle is S squared times the square root of 3 all over 4. So what is S? Well, S is, in this case, the sine of x. So we take our area, the area of this blue triangle, let me make this in blue. The area of our blue triangle here is going to be sine squared of x times the square root of 3 all over 4. Okay? All right, so this one's going to get a little interesting because of that sine squared. So we've got a couple things going on here. So we're going to integrate from 0 to pi as the square root of 3 over 4 times sine x, just rewriting it differently, dx, okay? So now we got to use some trig substitution. This sine squared is not a super easy one here, all right? So there we go. So let's get that square root of 3/4 out of there to start, okay? And what we're going to do is we're going to substitute here. Now let me do a little side work here. All right, so sine squared, we have this reduction formula, and the sine squared, well, let me write this down first. It comes from this. Cosine of 2x is 1 minus 2 sine squared x. And if you solve this for sine squared, you get 1/2 minus 1/2 cosine 2x. All right, let you kind of work that out there, okay? So we're going to substitute this here. This is the integral of 1/2 minus 1/2 cosine 2x from 0 to pi. Okay, dx. Well, that gives us this. I'm going to split this into two integrals. You integrate 1/2. You get 1/2 x. And we integrate this second part here. We'll need to do a little u substitution. And that's going to give us 1/4. You might want to work that out on paper there. The integral of cosine is sine. So this will be sine 2x. We used a u substitution there. All right. So a little substitution gives us a square root of 3/4 all over plug in pi minus 1/4 sine of 2 pi. Sine of 2 pi is going to be 1. No, I'm sorry. It's going to be 0, actually. Minus, now plug in 0. We get 0, 1/2 times 0, minus 1/2 sine of 0. Okay? And so finally, I think we're about there. Square root of 3/4 times. Now, sine of 2 pi is 0. That goes away. Sine of 0 is 0. That goes away. And obviously 0 is 0. So that's going to go away. So all we have is times pi over 2. So that gives us a square root of 3 times pi all over 4. How's that? All right. So there you have it, cross sections. Okay, if you have a triangle, you've got to kind of work out this formula. I guess you could memorize it there. All right, but it's pretty easy to derive. If you have a half circle, make sure you find the radius, which is half of it, and a square. Well, that's pretty straightforward, and those are pretty common ones there. These are not easy problems, so hang in there, work through it, and good luck.